Hello students, in this video we will be dealing about the second type of FET, which is the metal oxide semiconductor field effect transistor. This type of FET is also called insulated gate MOSFET. The name insulated gate means the gate is insulated from the entire structure in this type of MOSFET. When we discuss the structure, you can find that gate is insulated. The main difference between JFET and MOSFET is that gate electrode is separated by an insulating layer, which is an oxide layer. It can be SiO2 or SiO from the semiconductor substrate. So the gate is insulated by an oxide layer from the semiconductor substrate. That is the difference between JFET and MOSFET. Okay. There are two types of MOSFET. One is D MOSFET or the depletion MOSFET, and the second one is E MOSFET, which is called the enhancement MOSFET. The distinction between these two MOSFET is how the channel is affected by the oxide layer. It sometimes get depleted type channel, or it can be enhanced. So what happens to the channel by the presence of that oxide layer? That is the main difference between these two types of FETs. The first type is depletion MOSFET. Here we have a P-type substrate, silica substrate, on which two heavily doped N regions are implanted, fabricated on this. N plus represents these regions are heavily doped. Right? Now these two metal electrodes are connected to these two N regions as source and drain. Right? Now there is a silicon dioxide layer formed over this silicon P-type substrate, which is of the thickness of 50 to 100 angstrom. So this is the silicon layer or the insulator layer on which the gate terminal is fixed. So the gate is separated from this substrate with this insulating layer of silicon dioxide. Okay. Now an N channel is diffused between source and drain. So here we have a channel of N. N channel means the electron, more number of electrons are present in this channel between these two source and drain regions. Right? This process of making this channel is by the process of ion implantation, which is very precise and fine. So we can get a fine structure of channel by the process of ion implantation. Right? So G and the channel, so the gate and the channel are separated by an oxide layer. Okay, since at the gate junction there is no PN junction, BGS can be 0, positive or negative. That is the main difference from JFET. Since there is no connection between gate and the channel, there is no PN junction forming here. Right? So VGS we can connect VGS to be 0, positive or negative. In the case of JFET, we know that we can either apply 0 or negative voltages at the gate terminal. But here in the depletion MOSFET or D MOSFET, we can apply positive VGS also. Now, this is the figure again. It is the figure 10.12 N channel D MOSFET. So P substrate and the N channel. Right? Now, first of all, when VGS is 0, so there is no potential at the gate terminal, and we apply a voltage between VDS, D and S. That means since the connection is there between drain and source, if we connect a potential here, there is a current flow through this N channel. So that is the value of IDSS, which is the maximum value, not the maximum value, the value of current ID when VGS is 0, which is the IDSS. So at VGS equal to 0, IDSS flows through the channel. Now if we make VGS negative, if we make VGS negative, what will happen? When this terminal is negative in this oxide layer, there is a shifting of charges. So there is a positive region on the upper side of the insulating layer and a negative region on the lower side. So because of this negative region, the channel has a has some deformations. That is, the electrons in the, since the current in the JFET is due to the majority carriers, electrons in the n-type material induces positive charges. Okay, so positive charges are made on this n channel. So that means this region becomes devoid of majority carriers. Majority carriers are electrons in the n-type region. So here, since there is an induction of positive charges in this region, there is a formation of depletion layer in this form. Okay, hence the channel becomes less conductive, and ID, the drain current, decreases. That is, a depletion of majority carriers occurs. So when we apply a negative voltage to the gate terminal, the drain current starts decreasing, and we apply more and more negative on the gate terminal, the channel becomes less conductive and ID decreases. So this is the exact figure in your textbook, figure 10.12. This is the N-channel depletion type MOSFET, and this figure is channel depletion with the application of negative gate voltage, which I discussed earlier. These are the two figures. You can refer these figures to draw it in your notebook, right? And now we are in a position to find the VI characteristics or the drain characteristics. So this is the VDS x-axis and ID on the y-axis. So when we apply VGS equal to 0, this is the region, this is the variation of I with respect to VGS when VGS is 0. It is almost similar to the characteristic curve of JFET, and this value, the peak value or the maximum value of current, we represent it as IDSS. So this is the point. Then when we apply VGS negative voltages, we get the depletion mode, right? So when we go on increasing the negative value of VGS, the current decreases. So ID decreases, which we have studied. This is because of the fact that ID is decreasing because there are more and more depletion. The width of the depletion layer increases in the N channel region, and hence the conductivity decreases. Okay, now if we make VGS positive, what will happen when VGS is made positive? We get more and more n-type majority carriers, or the electrons are more and more available in the n-type N channel, and hence it becomes more conductive than when VGS equal to 0. In that case, it is called the characteristic curve will be above the value of VGS equal to 0, and the current increases above IDSS, right? And when VGS above the 0 voltage, we call it enhancement mode. So a depletion MOSFET or DMOSFET can be operated in two regions, either in depletion mode or in the enhancement mode. Depletion mode is when it is below 0 voltage, VGS below 0 voltage, and it is positive when positive value is applied. It works in the enhancement mode, right? So in order to work in the enhancement mode, VGS has to be made positive. Then more negative charges are induced in the channel, and hence activity of the channel increases above IDSS. Next is the transfer characteristics. Transfer characteristics is the variation of ID with VGS. So when we find this variation, you get a curve like this. So in the case of JFET, we get a curve like this only from IDSS to VGS off. Here we get this part, which is the enhancement mode. This region on the right side of the curve, we get the enhancement mode, and on the left side of the curve, we get the depletion mode. So VGS, what is VGS off? It is the gate source cutoff voltage at which ID reduces to 0. This voltage is also called the threshold voltage. So it is the threshold voltage at which the channel becomes 0, devoid of charge carriers, and there is no drain current passes the or crosses the channel. Right? This is the transfer characteristics of D MOSFET. So these are the figures. You can draw from this figure. This is the depletion region and depletion mode, and this is the enhancement mode, and this is the transfer curve for a VDS 10 volt. Okay. Now these are the circuit symbol. So this is the gate terminal. So we have a gap here which represents the insulated layer. So these are for D or E MOSFET P channel. So this arrow is towards the gate part and drain and source, and these two here, the substrate is shown separately as a 4-terminal device. In most of the cases, we represent it as a 3-terminal device, and the gate is internally connected to the source.